Hi, good evening, everyone. My name is Alex Medeiros, and I've partnered with Tom Ferguson, and we'll be presenting on quantum money this evening. So, what is quantum money? The whole idea here is to make an object, quantum money, that cannot be counterfeited and can be verifiably transferred offline without communicating with a bank or a network. Classically, this is impossible, as information can be trivially copied, right? For example, if we had Alice and she was trying to transfer $1 to Bob, Alice could also send that information to Charlie. And if Bob and Charlie can't communicate, they will both think this is a valid transfer of $1. But of course, Alice only has $1, and so only one of them should really receive the funds. Currently, all digital payment systems, from credit cards to crypto, rely on communicating across a network to solve this problem. However, it might be possible with quantum information, which cannot in general be cloned. So, let's go into the no cloning theorem to see how it might be possible to construct an object that cannot be counterfeited. The no cloning theorem is this consequence of the linearity of quantum mechanics, which is an interesting sentence. So let's dive in. To clone information, we want to construct this unitary operator C, maybe our cloning operator, such that C ket psi ket 0 would equal ket psi, right? You just see this psi get cloned into the second register. And this should work for all psi if, you know. So assume that C, our cloning operator, can successfully clone 0 and 1. We're going to prove by contradiction. So we'll just go through assuming this. And then if we tried to clone the plus state, so clone on plus, our second register should also become a plus. Okay, let's crank through the math. If we expand this plus to 0 plus 1, and then distribute the C, and then work on the assumptions that we made above, we'll get 0, 0 plus 1, 1. Ah, darn. Well, this is the maximally entangled state, which is not plus plus. And so we've shown that in general we cannot just clone some arbitrary state. And again, by the linearity of quantum mechanics. All right, so this brings us to Wisner's scheme. So Wisner is this guy who proposed as early as 1970, which apparently is before the no cloning theorem was even, published or around or talked about. He devised some scheme or proposed in 1970 and then eventually in 1983 with his paper Conjugate Coding, the first quantum money scheme. So let's go through here. In it, bills have two components. So every single banknote is two pieces, a key and a value, right? A unique serial number stored classically. Just think some key value data store where the key is this unique serial number and then the value is the quantum state, an n-qubit quantum state. And so Wisner would prepare each qubit in one of these four states, and that would make it very difficult if you had many qubits to just randomly guess. And the probability of creating some already existing bill, right, is probability half to the n. So as n gets large, we actually can make this sufficiently small. We can make it near impossible to duplicate or just create some random state that satisfies a bill that is already constructed. So that's Wisner's scheme, which again, this is pretty cool, but the fallback is that it is a private key scheme in that it needs a central authority to create the bills and to map the serial numbers and to store that mapping and for others to request, hey, what is this mapping, etc. So we really want this public key system. And so this is interesting. We can't really let the merchants verify the bills, as the information needed to verify a bill can be used to make new copies of the bill, at least in Wisner's scheme. So the scheme is still insufficient to have verifiable offline transactions, as the bank always needs to be involved. What we really want is this public key quantum money scheme where anyone can verify the validity of bills. In particular, the bank should have some secret information which allows it to produce new bills, and anyone should be able to verify whether a bill was issued by the bank. Many public key quantum money schemes have been proposed, but most of them have been proven insecure, and that is what we'll be going through in this slide, a story of broken schemes. So in 1983, Wisner comes up with this private key quantum money scheme where, he just makes a bunch of bills with a minus and a plus and a minus and a plus and a 1 and a 0 and all these random bills with this. But the fallback is, or the trade-off here is that you need the bank involved to verify it. Okay. Now in 2009, Aronson comes along, and he comes up with this first publicly verifiable quantum money scheme. And he used random stabilizer states. I didn't dig into what exactly this is, but eventually this was broken in 2012 by himself due to an invalid cryptographic assumption in the initial paper. So that's unfortunate, but 2010, Fari, he introduced quantum money from knots, which was a scheme that encoded superpositions of knots having the same Alexander polynomials, which are thought to be computationally difficult to derive. However, there's no security proof currently, and knots are not really studied in this cryptographic context, so it's hard to make these cryptographic assumptions or ideas because some of these mathematical ideas aren't explored in the space. So 2012 again, Aronson broke his own original scheme, but then came back with quantum money from hidden subspaces. But eventually this was also broken due to finding an efficient solution to the underlying hard math problem of finding the hidden subspace. So that's unfortunate. 2017, all right, Xandri coming on, introduced a new quantum object called quantum lightning, which neither the mint, like the bank or somebody, nor an attacker can create the same state twice. So he created this idea of a new object called quantum lightning, and created some instantiation of it. However, in 2021, Roberts broke Xandri's initial instantiation of quantum lightning. That doesn't mean it's impossible to make quantum lightning, but as it stands, nobody's done it. There remain a few promising schemes which have not yet been broken, but many of them, of course, rely on these cryptographic assumptions that have not been extensively studied. So, all right, maybe there's still some hope here. In 2021, Kane et al. Introduced a new framework for building public key quantum money schemes, which they proved secure against black box attacks. So let's dive in. What does this mean? Here are the key building blocks. Digital signature schemes. All right. So in a digital signature scheme, the bank can have a secret key and a public key. The bank can sign. Oh my. Yikes. 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 In a digital signature scheme, the bank can have a secret key and a public key. The bank can sign messages with its secret key, and anyone with the public key can verify the legitimacy of a signature without knowing the secret key. So that would mean that everybody would need this public key, but maybe you imagine that all merchants have it or something. So using this, we want to create a scheme where the bank can sign a quantum state using a digital signature on a particular measurement. Anyone can verify the bank's signature on the state because they have the public key. But it's difficult to create another state with the same measurement. This needs to hold, right? Then the combination of the quantum state and a valid signature is the quantum bill. And the bank doesn't really need to store what that valid signature is or what the quantum state is. They just need to sign that quantum state. All right. So to do this, we choose some set of unitary matrices U1 through UT in a d-dimensional Hilbert space. These unitary matrices need to be commuting. So UK times UK prime equals UK prime UK, right? That commute. This implies there's a joint eigenbasis, as we've gone over in class many times, ket psi I, where I equals 1 to d, such that each psi I is an eigenvector of each unitary matrix UK. So to produce a bill, the bank will prepare the maximally entangled state, and that means the maximally entangled state does not depend on the basis, which means it's equivalent to this, right? And we've written this a ton of times. So the bank then performs phase estimation on this state for each unitary matrix UK. This causes the state to collapse into a particular state, psi for some I. The bank then signs each measured phase. The state and the signature form the bill, right? So every time they get a measure, this phase estimation out, they look at it, they add it to the signature, they sign it using their key, and add it to the signature. So here's the verification. A merchant can verify a bill by performing phase estimation, just like the bank did originally, and confirming that the phases match the bank signature. This is pretty cool, right? Because phase estimation, as we've seen in class, does not disturb the state. So we're able to extract information without disturbing it. And so that's really sort of the basis of this. And here are the requirements. One, digital signature algorithm should be secure. Maybe that's no-brainer. 2, each eigenvector psi I has a sequence of eigenvalues lambda I k corresponding to each unitary matrix. Any pair of 2 distinct eigenvectors should have sufficiently distinct sequences of eigenvalues. And 3, it should be hard to prepare the state psi I for some I. And here's the idea. A successful forgery would require either, 1, forging the bank's signature on some illegitimate state. This is prevented by 1, like nobody else has the private key, right? So they can't, forge the bank's signature. Creating a distinct state, which has the same measurement as a valid bill. Well, this is prevented by 2. And for some legitimate bill, psi I, creating another state, another copy of the state psi is prevented by 3 because it's sufficiently hard to prepare this state. Okay, so we're about to wrap up here, but this system has been proven to be secure when the unitary matrices are modeled as black boxes. However, to use this in practice, we actually need to instantiate. We need to create these unitary matrices. And that is really where this problem breaks down. This is rather difficult, as the unitary matrices need to have enough structure so they commute, as we saw in the previous slide, but not so much structure that creating psi would be easy. So Kane et al. Proposed a promising instantiation based on quaternion algebras, but this has not been proven secure. And so in conclusion, we looked at Weiser's 1983 scheme, and it's secure, but it is a private key system, which makes it a little impractical and not really better than any of our current alternatives for currency. The first major attempts at public key quantum money, like Aronson's 2009 scheme and the 2017 quantum lightning scheme, were both eventually broken and proven to be insecure. And of course, it doesn't mean this is an impossible problem. And new, more complex schemes are still being proposed, often based on different, harder mathematical problems, such as the one proposed by Kane et al. Using quaternion algebra. A provably secure, practical, public key quantum money scheme is still an open problem and ongoing area of research. And so I am very excited to sign off here with our quantum money presentation. It has been an excellent course, CMSC 657. The homeworks were really fun. I'm excited for the final exam, and I think we learned a lot about quantum money here. So thank you. And here's some references.